Good afternoon, Collision Conf. Everybody ready for the last talk of the day?
Woo!
Yeah. And Twitch. Oh, look at Twitch. Thank you for being with us. We have a real treat. We have my friend and yours, Randall Hunt, talking about how to choose the right databases. But before I pass it over to him, I want to show one just choice quote from Twitch. Skull Crusher for Life says, if there's any way to record the larger screen, there's a lot of downtime. Somebody later says, Skull Crusher for Life has good ideas. I love online anonymous usernames, don't you? Okay, Randall.
All right. Hello, everybody. Thank you so much for coming today. We have a whole bunch of content to cover, so I'm just going to jump right in. So why do we use databases? And I'm sorry for the people who are in the front who are being blinded by this, but I want you to think back to the original database, the human brain. A bunch of organisms come together, muscles evolve, things happen, and we start this lossy compression algorithm for knowledge that is like our central nervous system in our brain. It's low availability because when your eyes are closed and you're asleep, you can't access anything. It's low fidelity because you don't have the greatest recall. Like I can't remember what I had for lunch yesterday, or I can, but like most people can't. And it's not good like at replicating data. Like the only way to replicate data is a very, very slow protocol, right? Like I have to tell you, I have to teach you, I have to say this thing, and that's how the data gets replicated to other brains. So then the Mesopotamians, they're like, hey, this kind of stinks, let's do something better. And they start writing on these clay tablets, and then the Phoenicians come along, and the Egyptians are like, clay tablets suck, let's use papyrus. And then Gutenberg makes a printing press, and then they spread lots of dangerous ideas all around the world, and everything is terrible. And then 1970 happens, and Larry Ellison is like, LOL, let's build a database. And IBM is like, let's build DB2, and SQL Server, and all these other things start happening, and we come up with this idea of normal form. Has anybody ever heard that term before, normal form? So if you haven't heard the term normal form, it's completely irrelevant in 2019, and you can totally forget it. No. What it is a way of optimizing the storage of data. So traditional databases, like the one over here, they are optimized for storing data in rows and columns. So you have attributes that are your columns. Anybody ever worked with Excel before? Pretty similar to that. The problem that these databases were originally trying to solve was that in 1970, a 1 megabyte hard drive was the size of the stage. It had to be pulled in with the truck, and it also cost like $100 million. I'm making those numbers up, but that ballpark. And what happens is you start using normal form to optimize the storage and not anything else. You're not optimizing for the access patterns. You're not optimizing for any particular type of like user-friendly goal. You're just optimizing for storage. And that is the same technology that we are using in 2019. And that's wrong. That's bad. We're not going to do that anymore. So Access comes along. Lots of people would argue that's not a real database. MySQL, Postgres, the proliferation of open source, and then the recession hits and nobody's doing anything. I'm just kidding. Lots of fun research happened during that time. But then in around like 2008 to later, you see this explosion of new databases. dbengines.com tracks 319 different database engines. So this is tracking all the job posts, all of the Stack Overflow questions, all of the common engines that are used and deployed around the world. And you see this explosion primarily because of the advent of the cloud. So commodity hardware is now available really, really quickly, whereas previously, if you wanted to requisition hardware for a database, you'd have to wait 4 to 10 weeks and convince your CFO to like blindly swipe the credit card for these giant servers. And you don't need to do that anymore. Now, if you want a server, you get it in like 2 minutes. We're going to talk about all these different databases, but let's break down the categories. On the far left, we have relational. This is the traditional kind of referential integrity, third normal form representation of your data. There are lots of cool things that can happen here. You have key value stores. So key value stores, some people would say Redis is a key value store. We're going to actually treat Redis and Memcached as in-memory stores, even though they are kind of key value stores. The key value stores that have persistence are things like DynamoDB. And then we have document stores. These are things like MongoDB. We have graph stores. These are things like TitanDB and Amazon Neptune. We have search. That's a very common category of like online application store. Elasticsearch is like the de facto standard there. We have time series databases, and I'm going to tell you about a new technology that we have for time series databases that really kind of pushes the boundaries as opposed to the more traditional representations. And then we have ledger databases, which are crazy cool and super useful for a couple of different concepts. The thing that I want you to take away from this presentation is that in 2019, you can have your database as a microservice. For many, many years, databases were very expensive, and we treated them as this one monolith that we would all commit to, and we would all share the same schema and the same structure. But now, the proliferation of compute and storage and the low-cost compute and storage that's available to us lets us treat the database itself as a microservice. And when you treat it as a microservice, you can have the data not in this like single canonical store that everyone has to access, this one source of truth. You can have it spread out to a bunch of different stores, and you can access it in whatever pattern best fits the need that you're trying to provide to your downstream users. So access pattern-driven development and purpose-built databases are the key terms that let you build really, really dope applications. That's a technical term, dope. So what are the kind of AWS real offerings for these categories? Over on the relational side, we've got Amazon RDS, Relational Database Service, very well named. We have Amazon DynamoDB, not as well named. We have Amazon DocumentDB with MongoDB 3.6 compatibility. We have Amazon Elasticache, which has Redis and Memcached managed. We have Amazon Neptune. We have Amazon Elasticsearch. We have Amazon TimeStream and Amazon Quantum Ledger Database. You can tell it's an Amazon product because we put our name in front of it. Alrighty, lots and lots of customers. This is an eye chart of all the different customers. We're going to skip over that. When I go out and talk to customers, I see kind of two main areas where people are migrating their databases into the cloud. And migration is an interesting story. Sometimes people are doing these lift and shift migrations, right? Where they are doing a DNS cutover at some point, a bog standard, like same schema, same everything, moving straight from like Microsoft SQL Server to Microsoft SQL Server, from on-prem to cloud. But a lot of times, you're doing new applications. You're doing greenfield stuff. So what will happen is larger customers will kind of come in and do these lift and shift migrations, but as they are able to split off these monolithic apps into a couple of different microservices, some of those microservices will migrate to new data stores that support the access patterns that they need and let them scale independently, which is a pretty kind of cool concept, and it's a good workflow for building and training, for building and adding new features to these applications. So we have this thing called DMS, Database Migration Service. What it'll do is it'll spin up a managed compute node that gets added to your existing cluster, whether it's on-prem or somewhere else. All you need is like a JDBC connection string or a Cassandra connection string, a MongoDB connection URI. You pass that in, it spins up a node that acts as a replica for that particular database instance, and it will do the cloning of the data, pull it all over into the AWS version, and it can even do schema conversions. So we have something called the SCT, the schema conversion tool. And what that does is it will allow you to translate from like a Postgres to a MySQL, from a Cassandra to a Postgres, from Cassandra to MySQL, from Cassandra to DynamoDB, from MongoDB to DynamoDB, from MySQL to DynamoDB. You get the point, right? It does these conversions, and it does it in an automated fashion. A couple things it won't support are things like stored procedures or specialized indexes. You know, Postgres has a couple really cool things. So it won't be able to do all of that, especially if the other database doesn't work. But it allows you to do these migrations with literally zero downtime, because you're just adding another replica, and then you're switching one replica over to the master. And you're saying, OK, the AWS node is my master now. You can shut down your on-prem one, and all is good in the world. So why do we have all of these databases in 2019? We have different applications. How many people were using the internet in 1975? 1985? 1995? 2005? Everybody. 2015? Yeah, so we have this giant proliferation of data. In 1991, humanity produced more data, in 2001, humanity produced more data every single day than all of humanity had ever produced in the cumulative history of time up until 1991. That is straight crazy. So we are generating today exabytes of data per day across everything. It's mostly Zynga posts and Facebook posts, but you know, pictures of my cat. But you get the point. It's a ton of data that wasn't around before, and that's why we need purpose-built databases now. We're dealing with millions of users, hundreds of millions of users. Does anybody use Duolingo to learn a new language recently? Duolingo is an app. They use Amazon Poly to synthesize the voice, but they also use Amazon DynamoDB. They have 300 million monthly active users. 300 million users. And scaling a traditional relational database to 300 million users as like a two-person ops team, not fun. Scaling DynamoDB is like, hey, throw more data at me, and then it just comes in and you do it. We have customers like Snapchat that are using DynamoDB to store their stories feature. Anybody use Snapchat? Okay, I don't really use it, but my niece does, and apparently there's this like crazy gender swapping face filter right now that's like all the craze, and it's all over Facebook. But these stories, what they do is they're ephemeral. They last for 2 hours, or for 24 hours, and then they get aged out. So this is literally terabytes worth of data, or even exabytes of data. And think about New Year's Eve or a sporting event like the World Cup. You're talking billions of events per second. Billions. Like, way too much data for a traditional system to handle. But for the cloud, that's an API endpoint that you're hitting. And you don't have to care about any of that. You just have to blindly swipe your credit card. And now we're talking about performance going from milliseconds into microseconds. You know, we want our data. We did a study a couple years ago for the Amazon.com retail site, and we found that a latency of as much as 400 milliseconds can drop your sales by 4%. So 400 milliseconds can drop your sales by 4%. So people want stuff faster. How many people navigate to a new tab while they're waiting for one to load? Yeah, so for the purposes of Twitch, that was 100% of the audience. Everyone agrees. No one has patience. We all have ADD. So then we have the ability to scale up. We've always had that. We can add more stuff to the server. We can add more storage. We can add more CPU. We can add more RAM. You know, we have instances now that have a couple terabytes of RAM, 12 terabytes of RAM. But you also want to be able to scale out. You want to be able to add more nodes. And then you want to be able to access your data anywhere, anytime. So you want data as close to your users as you possibly can get it. So every single region. We have 21 regions with 64 availability zones. You can put a database in every single one of those and have global multi-master. So that is Aurora. That's the storage engine I'll talk about later. So Airbnb, they use 3 different databases. And they use more than just this, but I'm going to talk about the 3 that they use. They are like born and bred in the cloud. So they started on AWS, and they remain on AWS today. And their usage has grown as their company has grown. And they use DynamoDB to manage a lot of their lookups and their personalized searches. They use Elasticache to do some of the rendering. So if anybody has looked at Airbnb recently, it's this kind of React app, or I don't remember if it's React, but it's a static web page, but they have a lot of like API requests for searches and like history that are coming in. And all of that is stored in Elasticache in a Redis server. Then you have relational data stores. There's the referential integrity stuff, the transactions, the user, you know, is booking on this date, confirmed. And they do that in RDS. One of the interesting things, they're actually thinking about moving all of that into DynamoDB, because DynamoDB supports transactions now. Duolingo, as I said, 300 million users. They use DynamoDB, they use Aurora, they use Elasticache. Lots and lots of cool things. OK, that's the core intro. Now we're going to dive deep on each one of these categories. Everybody excited for that? This is going to be good fun. All right, so traditional SQL is a TCP-based wire protocol. You use a JDBC connection string. It has very, very simple kind of, you know, this is it. It's like insert into table 1 values. I get like nightmarish flashbacks whenever I see this sort of stuff, because I haven't had to write SQL in a long time. And you know, you can scale up with individual instances. Like I said, you can add more RAM, you can add more compute. You can scale out with read replicas, but you're limited in the number of read replicas that you can support, right? Because of the consistency that MySQL is trying to guarantee, you know, you want your replica lag to be very small. So the more replicas you add, the harder that replica lag gets to manage. So we support scaling out to, I think, 15 read replicas on Aurora, and that's kind of how you scale your read workloads. But to scale your write workload, your only real option with traditional SQL is to like scale up. And then like people will say, oh, I can do application level sharding. I can throw like PG bounce in front of things, and I can redirect things to different nodes. But if you've ever had to actually manage that in production, it sucks, and you don't want to do it. So when you get to the point where you have to shard and partition your data, you're going to have a bad time. And then you have joins, which are really just a Venn diagram. So this is what it would look like if you were to model a hospital, right? You could have patients, you would have doctors, you would have the hospitals, you would have the treatments, you would have the visit, and then you'd have these giant kind of views of all of that data summarized and constrained by these foreign key constraints. So wherever you see these dots, these stars, those are constraints that are locking that table onto another table. And when you're making edits to these tables, it has to acquire certain write locks, or it has to check for different kind of things. And this can be slow. And it can be cumbersome to write some of these queries that go and touch all of these different models. So what people do is they build out these, this is a really straightforward query. All it's doing is like counting the number of, I guess, doctor visits that somebody had. And this is not trivial to write. So what people do instead is they write ORMs, object relational mappers. And we'll talk more about those later. So what does RDS do? RDS is the easy, scalable, secure, fun, great managed Postgres, managed MariaDB, managed Oracle, managed Microsoft SQL, managed Postgres. You get it. A couple of cool features that I want to point out. You can get multiple AZ availability. So AZs are availability zones. Quick breakdown of our regional topology. So in AWS, we have regions. Regions are geographically isolated pieces. So we have 21 of those currently, and we're adding more all the time. And these have, say, a couple of availability zones within them, 3 or more. So within those availability zones, those actually are typically multiple data centers. So when we say region, think availability zones, which are the availability model of an individual region. And then when you think of an availability zone, think of multiple data centers connected by 100 gig fiber. So 2-inch conduit fiber. We actually innovated every level of the stack. So we have like 6,000 plus fiber pairs packed into this one 2-inch conduit. We can do terabits of throughput between these data centers. It's really, really cool, powerful stuff. And that's only the beginning. We're always going to get better at that. OK. And then RDS, turning on that multi-AZ, that high availability thing, where you want to have one replica in one availability zone and one replica in another availability zone. That used to be something where you would have to go and call up 2 different colos. They would have to be peered. They would have to have some fiber wave between them. And you'd say, OK, hey, you 2 colos, I want to spin up one replica set over here. I want to spin up one replica set over here. And I want to join between all of these. Non-trivial thing to set up. And if anything goes wrong, you're dealing typically with a couple of different vendors. In AWS, if you want to do that, it's a checkbox, which I think is pretty cool. And if you want to scale automatically up and down, we have something called AWS Application Autoscaling, which is a combination of all of the different autoscaling features that we have across EC2 and CloudWatch and DynamoDB and RDS and all this. And you can measure the incoming network throughput. You can measure the incoming compute. You can make a metric on basically any of the values that are coming out of RDS and say, hey, when one of these values goes over this amount, I want to scale up. And I want to add another read replica. And we have service discovery and all that good stuff. So it will auto-discover those nodes, all the good things. OK, so traditional databases are great, but they've been around since 1970. So back in 2014, a bunch of really smart people at Amazon got around, and they were like, hey, let's reimagine the database for the cloud. And that's kind of how Amazon Aurora was born. And if you just want to explore a couple of cool techniques and tools, go check out the that was my the Canadian came out a little bit there. Go check out. Sorry, it's rubbing off on me. This is a wonderful country. Go check out the Aurora paper. It is fantastic. And there are a couple of different ones now. I think there are 4 different Aurora papers that you can read. And they talk about the underlying data technology that we use in this Aurora storage engine. So what is the Aurora storage engine? It's a MySQL and PostgreSQL compatible database engine that's built cloud native. So it's reimagining these databases as if they were always born and bred in the cloud. So what we do there is we separate the compute layer from the storage layer. So because we control all of the underlying hardware and we control all of the networks and the partitioning and all that, we are able to put this giant shared storage layer that all of these different compute nodes can talk to. This lets us do a lot of really fun things. So how many people have been working on a relational database and you needed a copy of production data? That ever happen? For Twitch, this is like 100% of the audience. Everyone's always done this. It's great. What will happen is, let's say you have 60 gigs. That's your production data. And you want to download all that. And then you got to spin it up. You got to test. You got to test the migration. Maybe people write migrations for Ruby on Rails apps, where they do it in Django. They use South. And they use all of these kind of migration scripts to alter a column or add a new foreign key constraint. And or ensure a new index. Doing that in Aurora, first of all, we support something called fast DDL. So if you wanted to alter a column in a traditional relational store like Postgres or MySQL, and you call like alter column, change this from an integer into a big int, or change this from an integer to a decimal, that can take 17 hours on like a terabyte of data. To do that in Aurora would be like 14 seconds. So it's several orders of magnitude faster, because what we do is we're able to push most of those queries down to the underlying storage layer. On top of that, if you needed to get that dev snapshot, all we're doing is we're moving a pointer that points at that, all that data that's stored in your production. We just create a pointer to that shared storage layer, and we say, hey, fork off from here, and this is now the dev. And we don't have to, the cloning, we can clone a database in minutes, whereas otherwise, copying 60 terabytes or whatever would take forever. So Aurora, extremely, extremely scalable, way more than the typical performance of Postgres or MySQL. Very available, very durable. And in fact, one of the things I want to talk about is that shared storage layer and the durability that comes with it, because we split the data into 6 different copies and small partitions. We send it all out to these different availability zones. So each availability zone has at least 2 copies of your data. And that protects you against these N+1 failures. So let's say we had a whole availability zone go down, we would actually be able to recover your data even if like there was one other underlying failure, right? Like let's say one whole availability zone goes down and then one rack dies. Because the data is copied in 2 different places, you get a lot of really good kind of performance guarantees. It's one of the fastest growing services that we have at AWS. We have people like the United Nations, BMC, Amazon, Verizon Wireless uses it. I don't know if anybody here is a Verizon Wireless customer, because we're in Canada, but Verizon got better in my house recently, so I'm sure it's entirely due to Aurora. All right, so those are relational data stores. Whew. How about NoSQL? I don't like the term non-relational. Sometimes people will refer to NoSQL databases as non-relational databases. I don't think that's right, because you still have relations in the data. So NoSQL data stores are taking a different approach to reimagining databases in the cloud. Instead of focusing on like separation of storage and compute, they're letting go of some of the constraints that are enforced by. So I think, they're letting go of some of the constraints that are enforced by traditional relational databases. And the reason they do that is when you let go of some of those constraints, you get a lot easier to scale out, because you're not needing to, you can rely on eventual consistency across the nodes. So SQL, optimized for storage, built in the 1970s, not like the most modern of languages. Normalized, supports ad hoc queries, can scale vertically, good for OLAP workloads. NoSQL is, these are kind of outdated, because a lot of NoSQL stories will now support aggregation frameworks. They'll support all kinds of different queries, and it's a little more nuanced than just use one or the other. So when we talk about a key value data store like DynamoDB, what we're doing is we have simple key value pairs that are going to be our partition keys. That's going to say where in the storage layer does this piece of information live. We're going to copy it to a couple different partitions, and then we're going to be able to deliver a lot of performance so long as we don't have hot partitions, right? Like if we have a good partition key, we can go out and we can say, hey, I want you to spread this across uniformly across as many nodes as you can. But if we don't, then we're kind of screwed, and we just have one node that's responding to everything. So this is what the attributes might look like. You would have a primary key, which would be a combo of like your gamer tag and then the type of information that you wanted. And there are a couple different ways of doing this. You can actually make the partition key like gamer tag, period, and then the type. And that can be one key. Or you could have a primary key and a sort key. And you're able to do table scans, you're able to do individual gets, and you can get different attributes based on those sub-queries. So DynamoDB, really, really interesting kind of approach. And I've talked about this yesterday in the machine learning APIs. The advantage of an API layer to access a database is not always you don't always realize it right away. So we've reduced the prices of DynamoDB several times. So we've removed entirely the cost of global tables. So global tables are global multi-master tables that you can spin up. And rather than have the change streams for those tables be charged, we just remove that charge. And in terms of improving the performance, over the last 24 months, we've completely rewritten DynamoDB on the back end. And no one's noticed because they're still accessing it through the same API layer. So we can drastically improve the performance, pass those savings on to the customer without the customer ever having to change a single line of code, which is an extremely valuable experience. And that's why I'm a big fan of having these APIs as kind of a proxy layer in front of the service. And I think we're going to get even better at that as time goes on. But what DynamoDB does, it's consistent single-digit millisecond response times at any scale with virtually unlimited throughput. Like I said, Snapchat uses it. Imagine New Year's Eve, you have billions of transactions happening. There are companies like Finra. There are other companies that use this at massive, massive scale. If you've used the internet recently, you've probably touched something that is using DynamoDB. It's serverless, which means you're not managing any of the underlying infrastructure. You are not managing the nodes. You're not managing, primary, the replica, all this other stuff. It's just you access it through an API. You're not having to manage the read capacity or the write capacity unless you want to. You can scale those independently of each other. So you can scale the read capacity all the way up if you're doing lots of reads and the write capacity very low. It's great for an analytics table. If you want to pull stuff in, we have something called Glue. And Glue will go and pull the whole DynamoDB table in. You can run some transform on it. And you can export it out to S3. You can do whatever you want. There's also auto-scaling for the database itself. So you can say, I want you to auto-scale my read capacity and my write capacity for me. And it will just read the metrics of the incoming database and then make changes over time. The other thing you can do is say, actually, I don't want to have to deal with managing capacity at all, and I just want to pay per request. So we have a pay per request model as well. So what does this look like? You've probably seen tables before. Tables are, we have items. Items have attributes. One of those attributes is the partition key. Occasionally, one of those attributes is a sort key, so the sort key is optional. You access the items by creating a query on the partition key and the sort key if it's there. And the sort key enables you to do things like begins with, between, contains, in, sorted, all that good stuff. And then the attributes you'll notice are sparse. So not every column needs to be filled. So I can have things that don't exist in some tables. And a lot of applications, you really only need one table because you can have completely different partition keys that are serving totally different needs. So you can keep everything in the one table if you really want to. You don't always have to do that, though. So how does it work? You connect over HTTP. You have global secondary indexes. You have local secondary indexes. Local secondary indexes are a very powerful feature that can let you get, pardon me, slightly faster queries. It's actually another view of the table. So you can have attributes that are only populated in the secondary indexes that you can query. You can add DynamoDB Accelerator in front of it, which takes those queries from single-digit millisecond into microsecond. And you have global tables with multi-region, multi-master. You've got transactions across multiple tables, so you can do a transaction. You just grab a context handler, and you're like, hey, I got multiple tables. I got multiple items. I want to be able to run these transactions. You have change streams, pretty rich query language. I will say it takes a little while to grok the query language. One of the things I love about MongoDB is the query language is so dead simple and beautiful and elegant. I'm super biased here. But I just think it's really well done because any developer with any experience can walk into MongoDB and pick it up and use it without having to learn SQL, without having to learn any complex query language. So this is an example. This is using the Python SDK. The Python SDK for AWS is called Boto 3. It's called Boto 3 because the Amazon River dolphin is called the Boto. I didn't name it. We can blame Mitch Garnett for that, a wonderful individual. And then we're going to create a resource. So the resource is going to be DynamoDB. We're going to create a table on that, and then we're going to just update some votes. So I built a little application that lets people vote on their favorite editor. I can kind of show you that now, maybe. Whew. Is that enough information? So you can go and run this demo right now if you want. Oh, boy, I got to plug in. I'm going to run out of battery. 1 second. Sorry. All right, so we're going to go over to this DynamoDB table. And if anybody wants to follow along, you're welcome to call this number or text this number or use this chatbot. Whee! Close. All right, so you'll notice that Vim, which is the best editor ever, has 903 votes. But that's not quite good enough for Vim. So what we're going to do is we're going to find this little votes table. And we're going to find this little votes table. We're going to go in, and we're going to change Vim to be over 9,000. Because memes and Twitch. And then you'll notice the application, small little update, now Vim has 9,001 votes. Beautiful, wonderful. That's exactly as it should be. We'll change it back to 903 just so you can see the other editors. And that's how easy it is to use DynamoDB. You can see I've got these vote users here. These are hashes of the people so that if someone calls in again and wants to use a different thing, it'll change their vote. And I think the whole application for this is about 30 lines of code. So with 30 lines of code, you can build a giant, infinitely scalable online poll. Fun. Like I said, because it's an API-backed service, you get all these new features coming all the time. And you don't have to rewrite any code to take advantage of them. You just suddenly get that performance increase. So I'm a big fan of that. We have companies like Lyft that are using this. We have companies like Capital One, Snapchat, and tons of other companies that are using DynamoDB. We use it very heavily internally in Amazon as well. But sometimes you want richer documents, right? Does everyone remembers like the transition from XML into JSON, right? Like that's a thing that we did as an industry, and it was beautiful. We should have done it sooner, but like we switched to JSON because it's more readable. It's a nice balance between compute friendly and human friendly. And as we did that, it became harder and harder as JSON kind of became the de facto interchange format to map those JSON things into a relational data store. So what we had to do was we had to write these weird ORMs. And so Django, everybody use that framework, or Ruby on Rails? You have these rich ORMs, like Spring. You get these huge ORMs that are supposed to translate these rich JSON documents into like 30 different tables in your relational database. And it just becomes hell to manage. So document databases really kind of rose about and became important because of the ease of use for getting the data from the web app into the database and then getting it back out the same way. So that was driven by access patterns. So imagine a user profile. We can add in new things. We can modify the documents. We can have everything be rich. We can create indexes on all of this. We have lots of people using document databases, Cassandra, MongoDB, all of these other ones. They use it for everything from like content management to user profiles to personalization to all manner of things. Anybody use Buffer app? One of my favorite things to do is to spot MongoDB object IDs in the wild. So Buffer app, if you've ever used it, what it allows you to do is it lets you go and talk to a couple of different social media accounts. So if you're an Instagram influencer, or if you're a wannabe influencer on LinkedIn, or like, I don't know, whatever other platforms people use these days, you can go and you can be like, hey, Buffer, I want you to stage and schedule this post for me. For instance, right before I came on stage, I scheduled one to go out live so that Twitch people would join. So I hope the Twitch people joined. And in the URL, you can see a MongoDB object ID, which is really fun. It's really fun to spot those in the wild and say, like, oh, I can tell when this user profile was created because MongoDB object IDs are increasing based on time. So I think MongoDB object IDs all turned 5 back in like 2015, and they're going to turn 6 in like 2021. So you can see like the hash of the object ID in the wild. Anyway, fun stuff. But managing these is difficult. It's frustrating, and it's lots of weird stuff to like manage. I worked with a customer called Disney back in 2013 or something, and they had I think it was 1,000 shards, so 1,000 different MongoDB shards, and they had a full-time staff of like 6 people just to keep that running, not including their data center folks. And then I worked with customers like Grindr, who also had thousands and thousands of shards, not thousands, but like hundreds and hundreds of shards of this data going all around. And you don't want to manage all of that. Like, you don't want to have to shard if you don't have to. So what you do is we reimagined the document data store in the cloud. So how do you build this in 2019 as opposed to 2008? And what we do is we decouple the compute and the storage. We distribute the data into smaller partitions, and we increase the replication. Does this sound familiar? Does this sound like Aurora? Good guess. Yeah. This might be a common theme occurring across all the new databases that we build, because it's a good model. So what happens here is, instead of doing this MongoDB write concern with, a write concern of replicated to the majority of the replicas, oops, we can say all of the writes are durable by default because it's going to be immediately replicated to all of these different availability zones with less than a millisecond latency, which is pretty darn cool. And it supports all the traditional MongoDB drivers and clients and everything, so you don't have to rewrite any code. All you need to do, change a connection string. And there you go, you're running. I will say it does not support geo-indexes yet, and it does not support all of the aggregation features yet. So if you're depending on certain aggregation features, check the list of compatibility. Don't just blindly replace this and then complain when it doesn't work. I will say all of those features that are missing are things the team is pretty diligently working on adding as fast as possible. I am particularly interested in getting geo-indexes in it. I built an application back in like 2010 called GitShots. Does anybody remember this? At one point, we had like 40,000 daily active users, and what it did is every time you did a git commit, it would take a picture of your face and then post it on the internet. And I had to take it down because I got sued. But the fun thing is, like, as soon as the statute of limitations runs out, I'll just bring that back up and spin it up on DocumentDB. All right, so now we're going to talk about in-memory data stores. In-memory data stores are data stores that don't have a persistence layer. And for people who have used Redis, I've had someone in the crowd before say, hey, Redis has a persistence layer. Redis dump is not a persistence layer. Like persisting by calling a command and syncing everything to the file system, that is not a persistence layer. In-memory data stores are things like Memcached and Redis, and they're optimized for serving stuff without you having to go and talk to disk. And you can build these on like i3 instances and tons of RAM, and you can have everything like going super fast because it never has to. It's basically, the request comes in, it talks to the NIC talks to the RAM, and the RAM goes, okay, cool, here, have your data. And you can do that stuff really fast, but you don't get the persistence. Lots of people use this. How many people have run Drupal? Have you thrown Memcached or Redis or anything like that in front of it? So for the purposes of Twitch, everyone who runs Drupal throws Memcached in front of it. Anybody run like aggregation service, and they store the results of those aggregations in Redis? High score table, Redis. Like this is a really common use case. You see this in all of these 3-tier web apps, right? Like so you'll have the request, you'll have the load balancer, the client, the load balancer. Load balancer can like route the request to the cache, or maybe the cache is being spoken to by the client itself. And then if the cache misses, then it'll go down, it'll talk to the database, and then it'll hydrate the cache with the new information, and then subsequent requests will be fulfilled by that cache. Really common thing. It supports very simple APIs, so stuff like this, get, set, set an expiry. Lots of different customers using this. Like I said, Airbnb, Team Internet, which is a domain parking business. McDonald's uses this. McDonald's is a little scary in the amount of personalization that they do now. Also, Domino's. Does everybody know like Domino's is actually a tech company? They are not a pizza company. Like they spent $2.5 million building the best recruiting video I have seen in my entire life. It made me want to go work there. If you Google Domino's tech recruiting video, you'll be very impressed. But they use Elasticache, they use DynamoDB, they use Aurora, they use Personalize, they use all kinds of good services. So Elasticache is a managed version of either Memcached or Redis. So Redis serialization protocol over TCP, strings, hashes, lists, sets, and sorted sets. It's only got about 120 commands. It's built by this Italian person named Anti-Rez who has lots of opinions, and he tweets about them all the time. I suggest ignoring that and just focusing on the great database. Please don't follow his Twitter. You get really angry sometimes. I do it because I like the drama, but if you don't like drama, don't follow his Twitter. But if you do, it's better than HBO. So then you get the pub sub features. So this is great if you're building like WebSocket applications or chat applications, all that good stuff. And it supports clustering via partitions, but those are blind partitions. They're not aware of each other. The client is the part that is making the call about whether or not to route the request to a particular partition. Memcached is about the same. Supports text and binary protocols. You can tell that in if you want. Really small number of commands: set, add, replace, append, prepend, check and set, get, gets, delete, increment, and decrement. And again, client blind partitioning. Search is really fun. Has anybody ever searched for something before? 100% of the audience, Twitch. All right, and what will happen here is with you'll have these documents. You'll create an inverted index, and you'll find these stop words. So you have a small little language model. Commonly, the most common version of this is like Solr or Lucene, and those are all powered by this other framework called libstimmer. And libstimmer will run. It'll find all the stop words. It'll do all the good stuff. And I got to speed up. So this is what a search looks like. You'll say, OK, I'm going to do a search for house, and then I'm going to get back these results. And these results will be ranked, and I will be able to pull in the data. Adobe uses this, MirrorWeb uses this, Hearst uses this. Managed Elasticsearch is the most wonderful thing in the world. Fun story, at SpaceX, we built a giant telemetry system on Elasticsearch. Worst decision of my life. Like, holy crap. I had to manage Elasticsearch myself for like 2 years, and I regretted every moment of it. So not managing Elasticsearch was the greatest day of my life. I remember turning off PagerDuty and deleting it from my phone. So Elasticsearch is written in Java, and the way that you find out what went wrong is you take the stack trace and then you scroll for 4 hours. I got like carpal tunnel syndrome just from scrolling up through these like mile-long stack traces. Luckily, you don't have to do that with managed Elasticsearch. All right, graph databases. These are really fun. So you can build graph databases in relational databases. But what we're focusing on with graph databases are the relationships between the nodes rather than the data on the nodes themselves. The data on the nodes is still important, but we're going to focus more on these rich relationships that we can query and get rich information from and drive recommendations and a better query model than what you would have to do in some crazy SQL query. So you have vertices, you have edges, and like I said, you can build this in a relational database. People have been doing this for years. But the problem is the query patterns and like bending your mind to create one of these queries, or better yet, teaching another new team member to write these queries is cumbersome, slow, and frustrating. So the graph data model works by taking something like Gremlin or Tinkerpop or Sparkle and RDF and saying, hey, let's re-envision how we could query these relationships. People use it for social networking. Anybody use Facebook? Yeah. Recommendations, knowledge graphs, fraud detection, life sciences, network and IT operations. We use it to recommend books. I'm going to show you an example of that in just a bit. So this is a Gremlin query. And what we're doing is we're going to say, grab the vertice of book 1, and then store it as a variable A. And we're going to say, find all of the people who have also purchased other books that also purchased book 1. And then we're going to remove ourselves, and then we're going to order by the rating, and we're going to output all of the names. So we have something called Amazon Neptune. Amazon Neptune is a managed graph database, and it's somewhat serverless in that you don't really need to like manage any of the infrastructure, but not fully serverless in that you still spin up nodes and you kind of see them, and you're still paying for idle and all that good stuff. So query billions of relationships, millisecond latency. Again, that's 6 replicas of your data across 3 AZs. Kind of common theme you're seeing. Really easy to write queries in both Gremlin and Sparkle. So I love Gremlin. I think it's a well-designed language, and I think it makes querying graph relationships quite easy. No one really uses it. I don't know why. I wish I would see more Gremlin in prod, but the thing I see in prod is actually RDF and Sparkle, and there's a reason for that. So this is a Gremlin query. It's saying like add a vertex, add of name Randall, add the property age of 27, and the property set, the single part here is not a comment on my marital status. It's saying I don't want to add in additional values on this one node. So instead of creating an array, I'm just replacing the single value. And I'm going to add another person, my friend Marcus, and then I'm going to add an edge that like knows Marcus from Randall to Marcus, and then we can query that. RDF is XML hell, again, and you store the data in triples, and then you write weird little SQL-like queries in order to query this sort of stuff. The reason RDF is used a lot more is it allows you to draw comparisons between the different data sets. So you can have multiple different databases all talking to each other, but they have a single globally unique identifier. So this is really good for like referential integrity across lots and lots of different data models. There's a company, Siemens Corporate Technology, and they build all these like turbines and all kinds of crazy cool machinery, and they track it around the world, and they use Neptune to query the status of all of these engines at any point in time. And they can find out everything they need to know about it, like when was it created, when was it built, when was it last serviced, who was the engineer who worked on it, and they can get all that information from like 90 different databases, but query it all in Neptune. Okay, really quick demo. Woo! So I'm going to create a retail demo application. So imagine an online e-commerce site. And we're going to use a key value store to store the catalog. We're going to use a graph store to do the recommendations. And we're going to create a product leaderboard with Elasticache. And we're going to provide search with Amazon Elasticsearch. Now, if you want to build this yourself, luckily you can. So Amazon, we have a thing called CloudFormation. And in CloudFormation, what will happen is you can go and launch the stack, and it's in YAML, I hope, and not in JSON. Yeah. So YAML specifies all the different things that are happening. So let me scroll down past all this. And you say, build a VPC, launch a node, launch another thing, launch another thing. It'll do all that. Luckily, this is already built. So I just have to go and find bookstore. And I can look at the output of this, and it says, go here. And this is my demo. And I've already got login and logout supported by Amazon Cognito. And I can search something, and it won't show up because that wasn't a real, what am I looking for? Kitchen. And we can go and look at the resources that are provisioned. So there should be a DynamoDB table here. So I can look at the cart. So these are 3 different tables. I've got one table for the cart. I've got one table for the orders. So these are the order history. This is the book ID. And this is the catalog. So I can go and change any of these titles if I want. And then we have recommendations. So I can go and look at these bestsellers. And this is a query that I probably should have warmed up beforehand. One of the things with Lambdas and VPCs is that you occasionally get a cold start, which is what's happening right now, which is why it's not rendering very quickly. But in the interest of time, we are going to, oh, there we go. And now the subsequent refreshes will be very, very fast. Ta-da! Because it's all going to be stored in Elasticache. OK, so that's the demo application. We've got 2 more databases to cover in like 2 minutes. This is going to be great. Everybody excited? All right. If you want to launch this, go here. I'll let anybody who wants to do this check out the slides later. As we scan your badge on exit, we will email you the slides. All right. So time series databases. Time series data is data that has the primary access of time. So stock data or humidity data in like a warehouse, or sensors. Things where time is like your access pattern. And so this is an example, right? You'll have this humidity sensor. And relational databases do not support this very well. This is a format that really is hard to shove into a relational database without kind of crazy manipulations of the underlying data store. So people have made modifications to the NoDB database engine in order to make time series work. It would be much better to just create a time series database, which is what Amazon TimeStream is. So this can collect data, millions of inserts per second. It can do trillions of daily events. It supports windowing functions, interpolations, a rich query language for SQL. It's serverless, so you don't have to manage any of the servers. And then we have ledger databases. So ledgers are things like HR, payroll, manufacturers, government, DMV. So we can take this ability to cryptographically verify the history of any sort of transaction by chaining them together, so that if you remove any of the previous nodes, the hash of that particular node is no longer valid. This is really, really useful, because if you ever have to get called up in court, a skilled database administrator could say, oh yeah, I could have gone in and edited the history. With ledger databases, they're append only, so you physically cannot edit the data without changing the hash of the currently stored version. So the history of that transaction remains true and pure. And in doing this on a blockchain is another common way of doing that, but the blockchains are slow. So how do you do this? You have an append-only journal. That journal shows you the current version, and then a hash, which is the hash of all the previous versions kind of chained together. So this, let's imagine we buy a Tesla, and so Tracy Russell is the new owner of a Tesla, and that gets put in, and now Tracy Russell sells that to Ronnie Nash, so we update that. We chain the 2 records together, create a hash, and then we get the history of the cars, and we can look up the previous versions. And then Ronnie Nash sells it to Elmer Hubbard, and now we have Elmer Hubbard, and we've got that chain. So we have this preserved history that's cryptographically verifiable across all the transactions. So QLDB is the solution here, and it's not called quantum because it uses quantum anything. It's just called quantum because it's smallest unit that you can atomically modify. So if you want to know more about building purpose-built databases and you want to hear from some customers, there's a lot of really, really good stuff out there. The core thing to take away is build based on your access patterns. Don't think about how you're going to store the data. Think about how you're going to access the data down the line. What is the most relevant information that you can return in a single request from a database that you can immediately render to the user? That kind of development, that kind of working backwards is really, really powerful. So if you want to learn more, we have a whole series on this called This Is My Architecture, where you can learn about all the different customers that we have that are doing good stuff. If you want to learn more, check that out. These are all the databases. More information here, more information here. thank you so much for your time. I hope everybody has a good rest of your collision.
Do we have time for questions from Twitch? 10 seconds. OK.
Do we have another show after this? Because we don't have any more talks, right? Yeah, let's just keep going.
All right. Joseph Ireland on Twitch asks, can SageMaker access any of these databases for their deep learning neural networks?
Yes. So you can talk in SageMaker to Neptune. So the way you deploy an algorithm in SageMaker is a Docker container. So who was Joseph Ireland was the person? So Joseph Ireland, if you want to have a document go and talk to, or a Docker container running on SageMaker go and talk to Neptune, you can do that because it's going to be provisioned in a VPC. But you're writing that code yourself. It's not like a pre-built thing. Any questions from the audience?
Anybody from the audience? Yeah. OK.
Yes.
What's the suggested way to do migration on NoSQL databases like DynamoDB?
The most common way of doing migrations on NoSQL databases?
Yeah.
So DMS supports NoSQL migration. So you can do Cassandra to Dynamo. You can do.
No, I don't mean like that. I mean like the schema got updated, right? So let's say you have like 5 fields.
Yeah.
And then
okay.
you
So
want
there
to
are two
add a
different ways
field
of doing
and
it.
then remove a field.
So doing migrations in a document data store.
Yes.
Gotcha. So like writing the migration script. So like the easiest way is a for each loop running on the database itself. Like that. Like you can do that. You can do that kind of crazy stuff. If you're talking about transactional kind of migrations where you have to acquire a write lock and make sure no one is accessing the database, most document databases don't really support that model. So
No, I don't mean like that. Like you can migrate the data like many times, right? Like you might have
Yeah.
I have like 10 migrations, right?
Yeah.
Let's say I need to roll back to number 6 and not number 9.
yeah.
I can't do that,
So
right?
no. So there's a framework called Eve built in Python, and they have a model that supports that kind of access pattern for MongoDB. So the thing that Eve uses in the background, I don't remember what it's called, but it's like core to that infrastructure, and they have the ability to roll forward migrations and roll backwards migrations in MongoDB. I don't know about other databases.
But you lost the data already, right? So like, let's say you
No.
deleted a key,
Oh, if you're
right?
saying
And
you're
then you
deleting
want to go
thing?
back, you lost
Yeah.
all the information.
One of
right?
the advantages of DocumentDB is you can roll back to any point in time.
Oh, okay.
So typically you only store like 7 days of that data, but you can actually extend that range to roll back to any point in time that you want. And you can do snapshots and restores. But yeah, no, if you're talking about rolling back a migration and you've got like a fork and you have like one branch that's gone off and you want to roll back to the previous schema, I don't think you can do that. That violates the laws of time.
We have another fun question from Twitch. Which
All right.
database is your spirit animal?
Which database is my spirit animal? MongoDB, for sure. Postgres is pretty beautiful. If you ever want to like learn a lot of C++, go look at the Postgres source code. It's quite well written. Now, not always. All right, that it?
Any other questions from the audience? Don't be shy.
Wonderful. Okay, thank you all so much for your time.